Welcome to this presentation on failure-driven development, or FDD. This is a different approach to software development, one that embraces failure as an essential part of the process rather than something to be avoided. Let's start with a fundamental principle. Failure is the best way to learn. Think about it. When things work perfectly the first time, what have you really learned? It's through our failures and mistakes that we gain the deepest insights and truly understand the problem space we're working in. There are fundamentally two ways of looking at development. Either we assume our code is going to succeed, or we assume it's going to fail. This basic outlook dramatically changes our approach to development and the processes we put in place. Your outlook determines your workflow. Consider these questions. How do you write software when you're convinced it will work the first time? And how do you write software if you're convinced it will fail? The answers to these questions shape everything about your development approach. Let's compare failure-driven development with current development workflows. The current workflow often tries to build software that works perfectly the first time, ignoring the possibility of changes, relying heavily on type checking and correctness proofs. In contrast, FDD builds in easy recovery paths from changes and failures and focuses on meta-design principles that make adaptation easier. Many workflows assume success from the start, but is that realistic? Let's examine what happens when we make this assumption. When assuming success, we are engaging in a waterfall workflow, one way, top to bottom, with no plan to iterate. Failure comes as a surprise and is hard to recover from. We construct type systems early and calcify them into our code. What happens when that original type system proves inadequate? Often, there's no change because it's too ingrained in the code and design. Waterfall development is the antithesis of failure-driven development. It's based on overconfidence, assuming the design will succeed. But early attempts almost always fail to completely solve the problem, and no recovery from failure is built into the workflow. Requirements and understanding of the problem space are usually incomplete, which leads to what we might call premature optimization. Now let's look at the alternative. Assume failure. What happens when we start with this mindset instead? Fred Brooks, in his classic The Mythical Man Month, observed a pattern: fail, fail, succeed. The first try typically fails because understanding is incomplete. The second try often fails because of over-engineering. And finally, the third try is just right. This pattern appears consistently across software projects. When assuming failure, we ask different questions. How can we fail fast? And how can we recover quickly? These questions lead to entirely different approaches and tools. Slide 12. Here's a fundamental truth of software development. The first several attempts at solving a problem will fail. We might as well accept this and plan accordingly. Consider the reality of software development. When software works, we abandon it, we ship it, and move on. When software fails, we continue working on it. This means that most of the time, we're working with failing code and failing designs. Failure is the norm, not the exception. What can fail in a software project? Virtually everything: requirements, design, architecture, engineering, implementation, and testability. We need strategies to address potential failure at each of these levels. Learning by failing is powerful. What do we need to learn? We need to understand what the requirements truly are, explore all aspects and gotchas of the problem space, and ensure testability. Think of this like designing automobiles for serviceability. We know maintenance will be needed, so we design for it. Plan for failure. Most of the time, requirements will change. Most designs will have flaws. Most implementations will need debugging and repairs. The number of failures is much greater than the number of successes. We should avoid clockwork implementations and optimization until the design has been tested and finalized. Here are numerous tactics to make failure less painful: iteration, isolation, divide and conquer, recursion, code generation, layering, indirection, solution-centric notation (SCN), the 5 whys technique, writing code twice, using multiple paradigms and languages, minimum viable implementation (MVI), you ain't gonna need it, fail fast, backtracking, portability, fact bases, and normalization. Let's examine some of these in detail. Iteration. The first few attempts might not be perfect. Don't waste too much time on complex type systems or writing flawless code. Instead, focus on creating a basic version that works. This approach is called the minimum viable implementation, MVI. Isolation is a key tactic. Create units of software that are fully isolated from one another. OOP-style encapsulation only encapsulates data but does not encapsulate control flow. Operating systems enforce isolation using extra hardware and software protection. Draw bounding boxes with ports around separate units of software, ensuring function calls don't flow beyond these boundaries. Isolation in operating systems uses extra hardware and software protection, but this isn't needed within a single app. We often see this as green threads and coroutines, but these are often overly complicated. Isolation was hard to implement in 1960, but is easy in 2025 with first-class functions and queue classes. Draw boundaries around separate units of software and poke holes in the sides of the boxes to allow data to flow in or out. These holes are called ports. Function calls must not flow beyond the bounding boxes. You must not call functions in other bounded software units, only call functions within the same bounding box. Units of software are called parts. Each part has exactly one input queue and one output queue, not one queue per port. This single queue approach prevents low-level deadlock within the underlying code and maintains events in order of arrival. Messages are pairs, tag payload, where the tag is the port name and the payload can be any data. For communication between isolated components, use send to send data out through a port. The main argument is a message event containing port and payload information, with other arguments as needed like debug info, such as tracer bullet data to follow messages through the system. Each part has exactly one event handler that processes one event at a time in order. Containers are composed of other parts and punt incoming messages to children parts. A container cannot process another message until all of its children are finished. The dispatcher decides which part gets to run at any one time. Function calls cannot force other parts to run. The dispatcher is effectively a loop that maintains a list of parts and runs one part at a time. This is similar to processes in operating systems, but without forced preemption and requiring much less code and hardware. Divide and conquer is another important tactic. Chop problems up into subproblems and use different paradigms and SCNs for each subproblem as appropriate. Function calling creates tight coupling, making it difficult to truly divide and conquer. Programmers often think they're dividing problems, but tight coupling creates clockwork, fragility, and interdependence. Code generation is a powerful approach. Fix issues, then push a button to rebuild everything. Don't write code that writes code. Don't write more compilers, write transpilers that map solution-centric notations to existing languages like Python, JavaScript, WASM, or Go. Tools like OhmJS, T2T, etc. are game changers for code generation. OhmJS can be used like a traditional parser or as a quickie parser similar to using regexes. These tools let you create nano DSLs or SCNs orders of magnitude faster than traditional techniques, enabling new improved workflows for software development. Recursive syntax is valuable. Lisp has a recursive nested syntax, while most programming languages are based on assembler-like, line-oriented syntax. Building new syntaxes that are recursive makes it easier to imagine and build new approaches. OhmJS and Peg make it easy to parse recursive syntaxes. Layering offers significant advantages over the infinite canvas approach. With infinite canvas, units are strongly coupled, and bigger systems mean wider canvases. With layers, units are loosely coupled, and bigger systems just mean more layers, with each layer containing a small, manageable number of units. For loose coupling between layers, use message sends between container parts with queuing and FIFO protocol. Disallow function calls between container parts. Function calling is LIFO in nature. Function calling does not follow a FIFO protocol. Recursive part composition allows nested recursive composition like Lisp lists that contain other lists. Containers are parts composed of other parts. From the outside, containers look like ordinary parts with ports, but from the inside, containers have gates that connect to ports of children parts. Indirection increases flexibility and makes it easy to rearrange parts. It's less efficient, but the approach is to get it right first, then optimize. Often, optimization isn't even necessary once the design is right. The 5 whys technique helps understand the heart of a problem. Start by asking about the problem, then rephrase each answer as a question and ask that question repeatedly. This process helps dig through layers of symptoms to find root causes. Writing code twice sounds inefficient due to our ingrained biases toward premature optimization, but it's actually more efficient when using appropriate languages. The first version isn't code, it's design. Iterate and refine this first version using dynamic languages, design-level types, REPLs, and appropriate control flow languages. Only when the design is finalized do you rewrite it using efficiency-biased languages. Solution-centric notations, SCNs, differ from traditional domain-specific languages, DSLs. DSLs are heavyweight and expensive to build. SCNs are lightweight, avoid generalization, are simpler to define for focused purposes, cheaper to build, taking hours instead of weeks, and emphasize thinking about the problem at hand instead of unrelated details. Minimum Viable Implementation (MVI) differs from Minimum Viable Product (MVP). With MVI, we skimp on efficiency but design the complete product, then test and refine the design before re-implementing with optimization. With MVP, though, we skimp on product features and implement only once, which often leads to design degradation. YAGNI, you ain't gonna need it, reminds us to avoid premature optimization and typing. Conceptual types can help during design, but machine-level types often hinder design with too much detail. Optimize only when you have proof you need it, and skip optimization if your MVI is fast enough. Fail fast. Divide problems, then attempt implementation of the greatest or riskiest unknown first. If an unknown becomes known, defer it and move to the next risk. If an unknown proves impossible, backtrack and redefine the problem. Testing can't prove that a solution works, but it can prove that a solution doesn't work. Achieving failure is easier than trying to prove success. Aim to fail sooner rather than later. Don't start out by building systems that are too big to fail. The scientific method is fundamentally a fail-fast methodology. A scientific theory is one which is falsifiable. We can't prove a theory correct, but we can disprove it. One contradictory data point can kill a theory. We should strive to disprove our theories early in development. Make it easy to go back to the drawing board. It's a vital part of the development workflow. Script everything so you can push a button to rebuild everything. When a design fails, repair the requirement, repair the design, regenerate, and try again. Multiple paradigms and languages should be embraced. IDEs must make it easy to switch languages and compose programs using many paradigms. The argument that using many languages adds complexity is based on biases from 1960s approaches to general-purpose languages. Different languages make it easier to express and to reason about different parts of problems. For multiple languages to work together, the transport layer must be simple, using strings, bytes, or other simple formats. This is sometimes called a narrow waist. Bolt many different parts together with this simple transport layer, like Unix using text lines ending with new lines, or using JSON or using HTTP methods. Portability through syntactic composition uses tools like T2T, ASTs, OhmJS, etc. to build many SCNs per project. Only the front-end SCN needs to be in human-readable format, while the remaining SCNs need only be machine-readable. This intermediate representation strategy lets you compose solutions by bolting stages together with a common front-end and specialized back-ends for different targets. This diagram illustrates portability through syntactic coupling, showing how human-readable syntax connects through machine-readable syntactic couplers to specialized output formats. Here's an example of syntactic coupling in PT Pascal, demonstrating how the approach was used to target multiple platforms including VAX and PDP-11 systems. Another example shows syntactic coupling in concurrent Euclid targeting VAX, PDP-11, and MC6809 platforms from a single codebase. Fact bases enable logic programming at a higher level instead of using lower-level loops. Many lower-level buggy operations can be replaced by simpler, more concise logic programming. Create SCNs that transpile MVI code to flat fact bases and logical assertions. Normalize everything to triples, relation subject object, and use relational programming approaches like Prolog or Datalog or mini-canren. Let the machine do the heavy lifting through a logic engine. Normalization makes everything easier to automate and script. Techniques like register transfer language, RTL, and orthogonal code generation, OCG, depend on normalization for portability. More normalized representations lead to more flexible, maintainable code. To summarize, FDD emphasizes automation and planning for failure, while our current workflow is like waterfall that plans for success with no tooling to handle failure. Manual work resists change, and time spent is not recoverable. Automated work accommodates change, regenerate code at the push of a button. Software is never truly finished. It just becomes shippable at some point. Type checking does not guarantee correct programs because it leaves out the iterative learning, design phase. Assume that you will need to change your mind. Use machines to help you change your mind instead of resisting change. If you'd like to learn more, please check out various platforms and resources. You can email me, visit my blog, watch videos, join the Programming Simplicity Discord, or follow me on other channels. I've included all the links in this slide for your reference.